In this lecture, we're going to discuss fractals. Fractals are an important part whenever you're talking about chaos and nonlinearity because they help us understand or model signals that are chaotic in nature. Now, we're going to start out talking about fractals in the spatial domain because it's a little easier to visualize, and then we'll move to the time domain and talk about fractal behavior in signals. So first of all, any object that is fractal must have self-similarity. So in other words, it has to consist of scaled replicas of itself. And it also must have what we term as fractional dimensionality, which is where the term fractal comes from. So this is a classic case of a mathematical fractal demonstrated spatially. You can ignore these circles, they're just there to focus the eye, but you can see we have these large triangles, and then each large triangle is split into three smaller triangles, and then each smaller triangle is split into three smaller triangles, and so on. So if we were to take this figure and blow it up or zoom in, we would see that each of these subfigures is an exact replica of the figure we're looking at. And we could blow that up and see that we had a subfigure of that. So these are basically scaled, identical dimensional figures. So basically this says what I just said. If any of the smaller triangles are magnified by a factor of 2, they would reproduce the larger triangle. So if we think about dimensionality, typically we have one dimension, we have two dimensions, which would be a square, we have three dimensions, which would be a cube. If we now split that into two pieces where n is a unit length, so if we now take 2 unit lengths, we find that in the second dimension that would be 4 units. In the third dimension, that would be 8 units. So notice that this is 2 squared, this is 2 cubed. So the dimensionality is basically the magnification factor or the multiplication factor raised to the power of the dimension. So likewise, if we took 3 units and then we squared that, we would have, and went to the second dimension, we would have n equals 9. We go to the third dimension, we have n equals 27. So basically, dimension is the log of the number of self-similar pieces divided by the log of the magnification factor. Now for Sierpinski's triangle, we have 3 self-similar pieces and the magnification factor is 2. So the dimensionality of Sierpinski's triangle is 1.58. There are lots of different examples. Cantor sets, the Menger sponge. There are fractals that occur in nature. Let's see if we can find another example. Let's see if this will take us to look at a nice picture of one that is not quite so straightforward. Yeah, here we go. So here's what we refer to as the dragon curve. We'll see if we can get a better picture of the figure. You can see that this one does not have quite the regularity of the previous example, but if we were to expand in any one portion of this curve, you would see that the subcurves are basically replicas of the existing curve. I'm going to move this to the side. We'll let that load for a little while and perhaps bring it up later when we have a cleaner picture of that. So there are other, and fractals can be divided into two groups. They can be deterministic or they can be stochastic. And one example is that if you have Brownian motion in a plane, that can be defined as a fractal pattern. Now, chaotic dynamic systems are sometimes associated with fractals. And objects in phase space, which, as you recall, we saw the attractor in the previous lecture, objects in phase space of a dynamical system can sometimes be fractal. And objects in the parameter space for a family of systems may be fractal as well. So one interesting data set or example is the Mandelbrot set. This contains whole disks. So basically you have a dimension of 2. And some of this is fractal terminology that we won't really get into, but basically the Mandelbrot set is one example. So even simple smooth curves can exhibit a fractal property of self-similarity. A power law curve also produces similar shapes at various magnifications. Let's see if we can pull that one up. My internet is really slow here, so let's see if we can pull that one up as well. So here's an example of a power law curve. And it does exhibit a fractal dimension because if we take any point, any sort of range on this power law curve and expanded it, we would find that we get a similar shape. So fractal is all about self-similarity. Here's that dragon curve with a little bit better resolution, or the dragon tail with a little better resolution. And you can find that as we blow this up, if you look, for example, at what's illustrated in the yellow here, that looks a lot like what the larger shape looks like. And then each one of these curvy tails, and I'm limited on how much I can zoom, but each one of these curvy tails, if we were to zoom in, this little one would look a lot like this big one. You can do similar things with maps. Coastline maps are the classic. If you look at a map of a coastline and you continue to blow it up, you find that blown up versions look very much like the original version. So it's all about scaling. There are some additional types of fractals. A lot of these you can look up yourself. They're fascinating to look at, very beautiful. The Lyapunov fractal is something that we looked at in a previous lecture. These are some prettier sort of surface models of a logistics curve illustrated in three-dimensional space. So this is kind of a surface model of some of the figures that we looked at previously, looking at trajectories. So this is also a fractal type set. Brownian motion is another thing, landscapes we discussed. So there are ways to categorize fractal behavior, but the general behavior is that you do have some scaling and some self-similarity. Here's a Cantor set. This is pretty cool looking. And here's another one of the dragon tail, or something a little bit similar to the dragon tail. And you can see just the overall pattern. There is self-repetition. So we could blow up one part. Here's another geometric figure. Brownian motion. Brownian motion is just the random movement of particles. So if you have a liquid or a gas and you look at three-dimensional motion, this is a thermal process. It happens when temperatures are above absolute zero. Things will move. And so Brownian motion is a simple stochastic process. And you can look at what Brownian motion looks like in XYZ dimensions. This one is bounded. So this is also exhibits fractal behavior. Here's a Mandelbrot set, another two-dimensional figure that exhibits fractal behavior. And then this is a classic example of a process in nature. This is just electrodeposited copper from copper sulfate solution. And you can see that basically here was the seed particle. The behavior of the growth of the copper crystal is a fractal behavior. Electrical discharges, high voltage breakdown. This was a high voltage applied to an insulator. The insulator broke down it was a volume kind of breakdown. You see it form this tree looking. This is also a fractal process. Now, self-similarity in a stochastic process means that the distribution function and the higher moments of the distribution function are identical. So in practice, what this means is if the mean and the variance are the same, the processes are assumed to be self-similar. So one way to define whether or not a signal is self-similar or fractal is to look at the mean and the variance. So how do you classify fractals? Well, the first thing you do is you extract the have exact similarity. So this would be the strongest fractal behavior. The fractal would appear identical at different scales. Quasi-self-similarity is a looser form of self-similarity where the fractal would appear approximately but not exactly identical at different scales. So your coastline would be one example. Fractals that are defined by recurrence relations are usually quasi-self-similar but not exactly self-similar. And then finally, statistical self-similarity is the weakest type of self-similarity, but in this case the fractal would have a number of statistical measures that are preserved across some scale. So most reasonable definitions of fractal would imply some form of statistical self-similarity. The fractal dimension is a numerical measure itself which is preserved across scale. So random fractals are examples of fractals that are statistically self-similar, but they're not exactly or quasi-self-similar. Here's an example of quasi-self-similarity occurring in nature. You can see this is Italian broccoli or it's a form of broccoli. This is a fern leaf. So I want to stop the video here and then we'll come back and talk about time domain signals. But basically in biomedical signal processing, we're concerned with time domain signals. And time domain signals can have a fractal nature, but to really talk about it, it's a lot less visual, and so it's not quite as intuitive. Time domain signals are two-dimensional, but they often represent two different quantities, time and whatever's being measured as a function of time. So unlike the spatial dimension of x and y, which both dimensions represent the same physical feature, time domain signals represent time in one dimension and some other physical property in the other dimension. So you have two different dimensionalities when you work with time domain signals.